You guys need another piece of paper for today. We're going to call this page 76, covalent Lewis diagrams. Here's your essential question. How are molecules constructed in a covalent bond? I'll have to pause it so everybody can catch up and get everything written down. Hey everybody, still not feeling great. One more day, promise. I'll be back. But let's talk about what we were talking about last week with our foldable, with our types of chemical bonds. In this first example up here, this is an ionic bond up here. And if you can see what's going on, this atom A over here is holding out its electron saying, here, don't you want this? Don't you want this? And atom B over here has his mouth hanging open saying, ooh, I really, really do. So what's eventually going to happen is atom A is going to give it up to atom B, because an ionic bond is a transfer of electrons. What's going on here in the middle, this is a covalent bond, and this is what we're going to do today and talk about today. In a covalent bond, you'll notice that they're sharing their electrons back and forth. Atom A is like, here, I'll let you try mine. And atom B is like, well, you should try mine too. It's like taking a bite of anybody's dessert if you go out to a restaurant. We both want a bite. So that's a covalent bond when the electrons are being shared. And then metallic, we didn't talk about in very great detail, but we will when I get back. In a metallic bond, you'll notice that they're about to play baseball. So you've got atom A over here with his baseball bat. You've got atom B over here with the baseball in his hand. He's going to throw the electron over here, and it's going to go flying out here somewhere really far away. If we remember the C of mobile valence electrons, meaning those electrons are flying all over, back and forth, which is why these guys are so malleable. It's why these guys are so much better at conducting electricity than others, because they're able to take the electrons and the electricity on one side of the metal and literally yank it through to the other side, making it a really good conductor. It's also why metals are shiny. If I tried to shine a flashlight down here, what's going to happen is my beam of light is going to get blocked by those free-flowing electrons, and they're going to hit my metal, and they're going to bounce off, and my metal's going to be super shiny. So that's a brief overview of all of our different types of bonds. So hopefully you felt successful yesterday. Don't get behind when I come back. If you haven't done squats since last week, you're going to really be behind. So please make an effort to do something outside of my class. Finish your diagrams. Make sure that you're raring to go. But if you remember yesterday, since this was ionic, this guy was the metal, this guy was the nonmetal, and the sodium gave up his electron to the chlorine, and everybody got their 8. But what's really important here is that sodium gave it up and became positive, chlorine gained it and became negative, and then we wrote FUs, like sodium chloride, with his 1-to-1 ratio. Well, today, the ratio goes away. We are going to give you the ratio, and you're going to come up with the drawing in the same ratio as the formula that we give you. These are some really good things to write in your notes. If you haven't been taking notes already, this would be a good place to start. Yesterday, we wrote down some properties of ionic bonds, so I don't think you need to write all of this down necessarily again. But the new part over here on the left, these are properties of covalent bonds. I just wanted to show you a side by side so you could see the opposite contrast that ionic and covalents have. The first thing we talked about yesterday with ionic bonds is that they had a very high melting point and how you could never melt salt. Well, a covalent bond is sugar. Sugar has a very low melting point. That's why if you hold your M&Ms in your hand for more than a minute, you're going to have chocolate all over your hand. So they melt very, very easy. They also boil very, very easy. It's how you make candy, is by melting and boiling sugar and then crystallizing it to make rock candy. Covalent bonds tend to be softer and squishier, so they don't make crystals like ionic compounds do. If you take sugar and you pound on it with a hammer, what do you make? Powdered sugar. And so it tends to be real soft if you put it between your fingers and you roll it around. It's real light and fluffy and squishy. Covalent bonds tend to be more flammable. There's ionic compounds don't tend to necessarily go up in flames, but covalent bonds do. A lot of covalent bonds tend to have carbon, hydrogen, and oxygen compounds. We call those CHOs, and CHOs are used in things like gasoline and fuel. Covalent compounds tend to not be as soluble in water, but if you think about sugar, sugar dissolves very, very well in water, so that's kind of hard to understand. But down at the bottom, sugar does not conduct electricity in water, whereas ionic compounds do. So if I put sugar in water and I tested it with an electrode, it's not going to light up the light bulb. A lot of us sitting here think that water is a good conductor of electricity. Well, I'm here to tell you that it's not, because it's covalent. The only things in water are hydrogen and oxygen. If there is not a metal present, it cannot possibly be a conductor. Ionic bonds are great conductors. Well, think about why. Half of the compound is made out of metal, and metals are good conductors. So it makes sense that ionic compounds like salt, when you dissolve it in water, is a good conductor. We also call those electrolytes. You've heard that word before when it deals with Gatorade. Gatorade has metal in it. Gatorade replenishes your energy when you've sweat all of your ions out. And so Gatorade would light up a light bulb. Pretty weird. Water will not. It's covalent. If you check out my pictures over here, yesterday this is what we did. Our metal gave up his electron to the nonmetal. Excuse me. And then we ended up with this positive ion being very attracted to this negative ion, and they got stuck together like glue. This is a much stronger bond than what we're going to do today. So today we're going to draw covalent compounds. It looks really similar. They each start out with their valence electron, but instead of somebody giving it up and somebody taking it, they share. They share. And there's this region right here in the middle that we call the region of overlap. That region where the two circles overlap and they share is the bond. That's where bonding is occurring. I know it's a lot to write, but you need to skip a line under your current notes, and I need you to write steps for writing covalent Lewis structures. This is going to be the easiest thing if you follow these 6 steps. And once you do this enough, you'll know these 6 steps and you won't have to look them up each and every time you try to draw one. But at first, you're going to rely on these quite a bit. So get writing. So the first step to writing a covalent Lewis structure, number 1, you're going to count all of the available valence electrons. This stands for valence electrons right here. And you're going to divide them by 2. And we'll do an example in a minute. Just get down the rules. Number 2, whoever's single or if it's carbon automatically goes in the center. Then we're going to bond your outside atoms in step 3. And in step 4, we're going to add valence electrons to the outside. Unless it's hydrogen, and we'll talk about him in a minute. Anybody extra goes back on the center atom. And then we're going to check for 8. In chemistry, you're going to find out we tend to make a rule, and then 5 minutes later we tend to break that rule. And so even though we learned the octet rule, saying that everybody wanted 8 electrons like a noble gas, you should be able to look up at the periodic table right now and tell the substitute which noble gas is stable but does not have 8 electrons. Can you tell him? Oh, you better be looking up there. I know you're still writing, but you should be able to know. Helium is has 2 valence electrons, and he is stable with 2. Remember, he only has 1 energy level, and so he's totally chill with 2 electrons. So he violates the octet rule by being stable with 2. All right, we're going to try an example. If you're not quite ready, have the sub pause before I start my example. Who needs a minute? Raise your hand. We can't see you. All right, here goes nothing. So underneath there, we're going to just do a bunch of examples. So here we go. Example 1. So I said this time we're going to give you the FU, the formula unit. But in this case, we call it a molecule. We're going to give you the molecule. The first molecule we're going to draw today is NF3. After Christmas, we're going to learn how to name it. That's nitrogen trifluoride. But let's go up and let's do our 6 steps. So it says, hey, find the available valence electrons and divide it by 2. So come down here to your example. You have to be able to, at this point, find nitrogen on the periodic table. He is in box 7. You have to be able to look at nitrogen on the periodic table and tell me what group he's in. He's in group 15. Then you have to be able to look at group 15 and tell me, how many valence electrons will group 15 always bring? And the answer is 5. If you can't do that yet, you're in the minority. Most of us can do that, so we've got to teach you that skill. You'll know it after this week. Then, find fluorine. He's in box 9 on the periodic table. He's in group 17, so he has 7 valence electrons, but that means he's got 7 times 3, because there are 3 of them. So nitrogen's bringing 5. Fluorine's bringing 7 times 3, which is 21. We add those up, and we get 26 valence electrons. So that is step 1. Then it says to divide that number by 2. So I get 13. This gets me my number of pairs of electrons. Go back up here to number 1 in your rule and say this is going to equal my electron pairs. Shout out to all my pairs. If you've seen that YouTube, it's funny. All right, so I know I'm hilarious. Number 2 says the single guy or carbon goes in the center. So we look at our molecule. Is anybody single? You should be able to look at that at this point and notice that nitrogen here is by himself. So we're going to draw him, and we're going to, you can do this underneath. I don't have any room, so I'm going to go over here to the side. But do this underneath our calculation right down here somewhere. And so our nitrogen is going to go in the center. So we have done rule 2. Rule 3 says we want to bond outside atoms. Going to take a little break here. What the heck is a bond? Out to the side of rule 3. Put a bond is 2 electrons shared. One bond is 2 electrons shared. So it would look like this. If I had element X and I had element Y, and they both were sharing each other's electrons, it might look like this. X brought a circle, Y brought a dot. How many electrons are between X and Y? 2. So since there are 2 electrons being shared, we would call that a bond. And so another way you're going to see this is X with a line in between Y. That stick in between X and Y represents that bond. This is not bad stuff to write down somewhere next to rule 3. So when X is bonded to Y, when your brain sees that stick, it's supposed to automatically think of these 2 electrons in between being shared. And so you might see it as dots, you might see it as lines. We're going to talk about both of those in our examples, but we just needed for a second to talk about what is a bond. It is when 2 electrons are being shared in a covalent bond. So on number 3 it says bond your outside atoms. Well, I look over to my compound in example 1 and I notice that there's 3 fluorines attached to this nitrogen. So we're going to come over to our picture and we're going to bond a fluorine, bond a fluorine, bond a fluorine. Underneath that picture, we're going to draw a second copy of this picture, but we're going to draw it differently. We're going to draw the nitrogen, and we're going to draw the 3 fluorines, but this time, instead of drawing the lines, let's draw the dots. Okay, and in these, I don't do dots and X's like I did yesterday. It gets really confusing. I did it for years, and kids were lost for years. 3 years ago, I went to these 6 steps, and I went to all dots. Beautiful. This will be so much easier, so trust me. In between nitrogen and fluorine, there are 2 shared electrons. So draw those 2. And then there's 2 more at the bottom, and 2 more on the side. So far we have 2 different representations for NF3. They both mean the same thing, but they're just using different methods to get there. Okay? So we have done rule 1 by calculating our pairs. Rule 2 by putting our single guy in the center. Rule 3 by bonding our outside atoms. Now we're going to go to rule 4. We're going to add valence electrons to the outside. And it says except hydrogen. We don't have any hydrogen to worry about, so we're going to ignore that part. So we're going to add valence electrons to the outside. Now let's take a break. Look, we had to use 13 pairs to make this work. So far, we've used 1, 2, 3 pairs. 1, 2, 3. So always keep an eye on your electrons. So we're going to use 4 on fluorine, 5, 6. because if you remember, the whole goal was for everybody to become stable. So what you're looking at right now is fluorine, and if you think about it, inside this circle right here, fluorine has 8 electrons. He's got 2 inside the stick or the bond, and he's got 6 on the outside. So fluorine got his 8. Even though he only brought 7 valence electrons, he's sharing somebody else's, so he's stable. We're going to come down and do it to our bottom chart too. So 1, 2, 3, 4, 5, 6. So we add those 6 to the outside, and again, if you look inside that circle, it's a little easier to see with dots. Fluorine has his 8. So we're going to go and we're going to do that to all of the fluorines. I'm going to do it to this guy up here on the right. 1, 2, 3, 4, 5, 6. Then go down to the bottom. 1, 2, 3, 4, 5, 6. And then our bottom fluorine. 1, 2, 3, 4, 5, 6. And at the very bottom, 1, 2, 3, 4, 5, 6. Everybody caught up? If we drew circles to check for 8, fluorine's got 8, fluorine's got 8. So all of our fluorines have achieved their stable octet of 8. So now let's count electron pairs. So here's 1, 2, 3, and then on the outside 4, 5, 6, 7, 8, 9, 10, 11, 12. So in my head I'm saying I've used 12 pairs. So I come over here to where I had 13 pairs and I subtract 12. Well, that leaves me 1 pair left. I have 1 more pair to place. And if you look at number 5 say any extra pairs go on the center. Let me make those a totally different color so you can see what we're doing. Alright, so I'm going to add my extra pair to the center. So there's my 2 orange last pair of electrons there. And I'm going to do the same thing down at the bottom. So look at number 6. 6 says check your octets. Well, we already checked our octets for fluorine 1, fluorine 2, fluorine 3. But let's check our octet for nitrogen. I know it's hard to see with all of my drawing here, but inside that huge circle, let's count. There's 1 pair, 2 pair, 3 pair, 4 pair. It might be a little easier for you to see on the bottom one, so let me draw the circle around the bottom nitrogen. Check out the dots. There's 2, there's 4, there's 6, there's 8. So nitrogen got his 8. So let's take a moment and think about how these drawings are so different than yesterday's. Yesterday we were transferring electrons and we had charges, we had brackets, we had arrows. Today we have none of that. We literally have sticks and we have dots and we hook everybody up and they overlap and they connect. So these are all connected. So this is easy to understand why they bond, because they literally are overlapped and connected. And so in this region where they overlap, there's 2 electrons inside that region. And so that is the bond. Let me show you this to you prettier. So if we cleaned this totally up, our end product would look like this. Nitrogen bonded to fluorine, 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 and then extra pairs on the outside. And so we used our 13 pairs of electrons. We checked for 8. Everybody was stable. So this is what I call the structural formula. Label that next to your drawing with your sticks. Anybody that has sticks is considered a structural formula. Let's do a couple more examples. So in example 2, let's do SiH4. So you're going to have to look up at your rules because they're not on my screen. But rule 1 says find your available. Silicon is in group 14 with carbon, so he brings 4. Hydrogen's in group 1, so he brings 1. But there's 4 of them, so I have to multiply that by 4. Add those together, and I have 8 valence electrons. Divided by 2 is 4 pair. So I only have 4 pairs of electrons to play with this time. Rule 2 says your single guy goes in the center. So that's silicon, Si. We'll do both drawings side by side. Rule 3 says bond your outside atoms. So there are 4 hydrogens sitting outside of the silicon. So I'm going to bond my 4 atoms. I'm going to do the same thing over here on this drawing, but this is technically called the Lewis dot structure on the right. So this is my structural formula. This is my Lewis dot formula. You're going to see it both ways, so that's why I want you to see it as both. The test has both, the CBA has both, the final exam has both, so you need to know this. So check out what we're going to do. We are going to put pairs in between each one to represent that bond. 1, 2, 3, 4. Alright, so there are 4 pair of electrons between each hydrogen and silicon, and the same thing's represented on your structural. Now, take a look at number 4. Number 4 says, put your extra pairs on the outside atom. But then it says, except hydrogen. So, hydrogen's kind of weird. Hydrogen, if you'll remember, only brings 1 electron. Well, if he gains 1 more electron, who does he look like? He looks like helium with 2 valence electrons. So because he looks like helium, he is considered to be already stable with 2. He doesn't need any more. So whenever hydrogen is on the outside, we skip step 4. He is considered to be stable. He is stable with 2. Hydrogen is stable with 2. Stable with 2. Stable with 2. They don't need any more. Rule 5 says put any extra pairs on the center atom. Well, now we got to look at our pairs. So look up here. We had 4 pairs of electrons to play with. Look down here, how many did we use? 1, 2, 3, 4. 1, 2, 3, 4. Well, they gave me 4 pairs and I've used them all. So I can't do step 5 either. So I don't have enough electrons to put anybody else on the center. So then I go to step 6 and I check for 8. We've already said that hydrogen is stable with 2, so he's violating the octet rule. So now we have to check silicon. So when I draw my circle around silicon, excuse me, when I draw my circle around silicon, you'll notice inside the white circle there are 2, 4, 6, 8 electrons. And so we are finished. This is the structural and the Lewis dot formula for SiH4. And it's as easy as that. Now I'm going to throw you some curveballs. Are you ready? Let's do example 3. See how far you can get on your own. We're going to do bromine 2. So the only reason this one's weird is only because I gave you one element. And so people tend to freak out a little bit. So what would you do? You'd find your available, multiply by 2, divide by 2 to get your pairs. So you have 7 pairs. So we did step 1. Step 2 is put your single guy in the center. Well, don't really have a single guy. I have bromine twice. So there's not really a center. It doesn't really matter who you decide is your center. So you're just going to draw one. And next to it, you're going to draw another one. Step 3 says bond your atoms. So I bond them. I'm going to do it both ways. And then step 4 says put your extras on the outside. Well, I had 7 pairs. I've used 1, so I have 6 left. 1, 2, 3. He's full. 4, 5, 6. He's full. So then step 5 says put any extras on the center. Well, let's count electrons. How many pairs did we use? 1, 2, 3. Don't forget the bond counts as 4, 5, 6, 7. So I've used all 7 pairs. I don't have any extra to put on the center. So I skip step 5 and I go to step 6, check for 8. So you should notice that there are 8 inside the left circle and 8 inside the right circle. And we're done. Let's do example 4. I'm kind of making this one up, guys. This doesn't exist. But if it did, we're going to draw it. Sulfur 2. You think it's going to look just like the one at the top, but here's where it gets weird. Sulfur's only bringing 6 valence electrons times 2, which is 12. So I only have 6 pairs of electrons to work with, which is going to make this really tricky. So we set it up very similar. Put your sulfur, bond it to your other sulfur. I neglected to go up and put my valence electrons on my Lewis dot for bromine over here. Sorry about that. Finish it off so it's not sitting there halfway finished. Alright, got all my dots over there. So back to sulfur. I've got sulfur bonded to sulfur. Put the extras on the outside. Here's where you have to be super careful. You're only allowed to use 6. I already used 1 in the center. So this is actually pair 2, pair 3, pair 4, pair 5, and pair 6. So then we put anything extra on the center. Well, I definitely don't have anything extra because I've just run out of electrons and I haven't gotten to fill sulfur's octet. So he only has 6 pairs of electrons here. Well, that's not going to work. So in your notes, draw a little cloud and write, beware of the Cenops monster. It's very scary. Trust me. Cenops stands for, you ready? Carbon, nitrogen, oxygen, phosphorus, sulfur. When you have one of these trying to bond, a lot of the times you're going to end up short. So watch very carefully. If you're snoozing, poke your neighbor. Make sure they're with me. Don't hurt them. Here we go. Ready? So I'm going to circle anybody who has their 8. This sulfur has his 8, but the other sulfur does not. So look what we're going to do. I like to circle the one who has 8. So the one who has 8 is going to move some of his outside electrons to the middle. So let's pick some. Let me pick these 2 guys. It doesn't matter who you choose. I'm going to pick these 2 electrons and I'm going to move them to the center. And I'm going to create what's called a double bond. And so really, these electrons on the outside go away. So now, when you look at this guy, and you circle the other sulfur on the right, now let's figure out how many electrons are on the right. It used to be 6, but now it's 2, 4, 6, 8. So everybody's octet is full and stable, and it's a double bond. So it might look like this if it was all pretty. Sulfur, double bonded to sulfur with 4 electrons on each side. In your notes somewhere, you need to point to that and call that a double bond. So in a double bond, think about it. How many electrons are in the center? Well, if each line is 2, 2 times 2 is, there's 4 in the center. And so these aren't the only guys that double bond, but when you see one of those and you're having trouble getting your 8, that's your clue that, oh, I bet there's a double bond somewhere. Notice we just moved one set of electrons. We didn't move a bunch of electrons around. We just moved one set. Let's try one more. All right, last one for today. If I haven't already run out of time, I'm about to, I'm sure. Example 6. Let's do C2H2. So I'm going to find my valence electrons. 4 times 2 is 8, plus 1 times 2 is 2, for a total of 10 valence electrons, or 5 pairs. Rule 2 says put your single guy in the center. Well, I don't have a single guy. I've got 2 carbons, and I've got 2 hydrogens. But if you look at Rule 2 carefully, it says, or carbon. Put carbon in the center. Well, I've got 2 of them, so it doesn't matter. So you can put one or both. Call it your center. Bond them, of course. So I've used one of my 5 pairs. Rule 3 says bond your outside atom. Bond, bond. Rule 4 says put your extra pairs on the outside except for hydrogen. Well, I've got hydrogen, so I can't put any extras on the outside. And so I'm finished with hydrogen. Hydrogen's stable. Hydrogen is stable. They both have 2. So then Rule 5 says go back and put your extra electrons on the center. Well, first let's figure out how many we've used. We've used 1, 2, 3. So I come over here to where I'm keeping count. I had 5 pairs. I have used 3. That leaves me with only 2 left. So I'm going to put them on the center. Well, you've got 2, so spread them out. I'm going to put maybe 2 right here. And if you wanted to, you could put 2 right here to spread them out. It doesn't really matter. So I've done Rule 5, which says put anything on the center. Rule 6 says check for 8. Well, we know hydrogens are stable with 2, so they've obeyed their exception to the octet rule. But if I go and I put a circle, watch this, around this carbon, how many are inside my laser circle here? Well, I've got 2 bonds, which is 2, 4, and then I've got 5 and 6. Well, carbon does not have 8, so he's not stable. Same thing with this guy. This guy has 2, 4, 6. He's not stable. He needs 8. And so we've got to find a way for both of these carbons to get 8. So beware of CNOPs. Carbon's on the list. So we're saying that he tends to move electrons to form multiple bonds. You can't move anything inside these hydrogen circles because they're already full with 2. So nothing can come inside those circles. So I've got to move electrons that are on this middle portion here so I can get 8. So watch what I'm able to do. I'm going to take these 2 that are just sitting there doing nothing. I'm going to move them to the center and make a double bond. So these guys really and truly go away. They're not there anymore because they're in the center. Well, what did that do? Well, if you can look here inside my white circle, now the carbon on the right has 2, 4, 6, 8 electrons. So he's able to be stable. But if I did the same thing with my laser to this left carbon has 3 sticks. So that's 2, 4, 6 electrons hiding in those bonds. He's got 6 electrons. Well, he's not stable. So we need somebody to move inside this circle to help him out. So watch what I can do. I can go grab these that are on the outside, and I'm going to move them in to create what's called a triple bond. And those go away. So now, when I draw the new white circle, there's 2, 4, 6, 8 on the left, and 2, 4, 6, 8 on the right. Write in your notes, this is called a triple bond. How many electrons are in there? 6 shared electrons. And so it would look like this when it's all cleaned up. H, single bonded to carbon, triple bonded to carbon, single bonded to H. That is enough for today. I'm not going to give you homework, but by gosh, your polarity and electronegativity worksheet should be finished from Friday, and your ionic bonding diagrams should be finished from yesterday. When I walk in that door tomorrow, not going to listen to the whining, they're due. There are other chemistry teachers that would love to help you after school or before school. I will be there at 6:50 tomorrow morning. I expect to see your face if you are having a hard time. Love you. Be good. Stay seated. See you tomorrow. Bye.